Okay, so we discussed drawing Lewis structures for both simple structures and expanded octet structures last class session. Today we're going to be looking into the nature of chemical bonds and starting to describe the bonds found in molecules in terms of polarity. And in order to describe the polarity of a chemical bond and the polarity of our molecules, we're going to look at a concept known as electronegativity. So electronegativity is a measure of how readily an atom attracts electron density in a chemical bond. So an element that is more electronegative will pull more of the electron density found in a bond towards itself. Electronegativity increases as you move up the periodic table, a small n value. And electronegativity also increases as you move to the right on the periodic table. The greater number of protons you have, the larger your effective nuclear charge. The electronegative elements are primarily going to be our nonmetals on the upper right-hand side of the periodic table. To help everyone along with this process, we've created a shorthand hierarchy, an electronegativity hierarchy of common elements. So of course, fluorine is the king of electronegativity, and following down from that, we have our oxygen, nitrogen, chlorine, and bromine. And as we see in the general trend, as we move up the periodic table and as we move to the right across the periodic table, our electronegativity increases. Now, we're going to use differences in electronegativity to start to describe how electron density is distributed in our chemical bonds. One important thing that I'd like to remind everyone from this table, and one important implication of this table, is if we compare, for example, carbon and hydrogen have a very, very small difference in electronegativity. So a carbon-hydrogen bond is considered functionally between two atoms with about the same electronegativity. Another interesting thing to note is if we look at a carbon-phosphorus, or if we compare the electronegativity of carbon versus phosphorus or boron, what is more electronegative, carbon or phosphorus? Carbon, yeah. This is important later on when we discuss the nature of a carbon-phosphorus bond and how compounds containing carbon-phosphorus bonds react. Okay. So, continuing on with this idea, let's talk a little bit about the continuum of chemical bonds. Depending on the difference in electronegativity between our bonding atoms, or our delta En, this delta En is the difference in electronegativity. So depending on the difference in electronegativity between the atoms in our bond, we can either have a non-polar covalent bond, a polar covalent bond, or if we cross a certain threshold, an ionic bond. Now, if our difference in electronegativity is less than 0.4, we have a pure covalent bond. And this can be considered functionally an equal, even sharing of electrons. There are two major cases where this comes up in this class. You could have a compound containing two atoms of the same element. So for example, looking at a chlorine-chlorine bond, the electronegativity of chlorine is approximately 2.8. So if we calculated our difference in electronegativity, 2.8 minus 2.8 would give us 0. So our difference in electronegativity is 0. Both of the chlorine atoms are pulling on electron density in our chemical bond with equal strength. The other major case this comes up is when we start to look at carbon-hydrogen bonds. So carbon has an electronegativity value of 2.4, and hydrogen has an electronegativity value of 2.1. Now, I don't want you to memorize the exact electronegativity numbers. That's not needed. What I want you to memorize and what I want you to understand are the qualitative differences in electronegativity between different atoms. So our CH bond, our difference in electronegativity is 2.4 minus 2.1, which is 0.3. So this is less than 0.4. So we can consider CH bonds to be functionally non-polar. There's a relatively even sharing of electron density in this carbon-hydrogen bond. Now, where things get a little bit interesting and where the majority of our organic compounds exist are in the polar covalent bond domain. If our difference in electronegativity is greater than about 0.4, we have what's known as a polar covalent bond. This involves an unequal sharing of electrons. So for example, in carbon monoxide, which looks a little bit like this, we have a carbon-oxygen triple bond. Now, this electron density found in our carbon-oxygen triple bond will be allocated more on our more electronegative atom. So oxygen has an electronegativity value of approximately 3.1. Carbon is approximately 2.4. So our difference in electronegativity is about, one moment, is approximately 0.7. Yes.
So you said 0.7. Are you writing negative 0.7?
I'm going to write the approximate symbol. There's just one moment. There's a small amount of lag in the actual projector screen. Let me show that clearly.
Okay, so then that brings me to the next question.
Yep.
It might be a dumb question, but so we always make sure we calculate these to where we would always get a positive number.
Yes,
Right?
the difference in electronegativity will always be positive, and we're concerned more with the absolute value.
Okay.
So even if you flipped,
so we can take absolute value.
Yes.
So then, but we always plug in the first element, right? So the most central element first when we're doing this calculation.
You can. It doesn't matter the order because it's an absolute value.
value.
Yeah, but yes, that's a perfectly reasonable question. Yeah. So looking at this idea, since oxygen is more electronegative, where is the majority of our electron density in our bond going to prefer to lie? On carbon or oxygen? Oxygen. So if we were to draw a description of how our electrons are distributed, we draw a large amount of electron density on oxygen and a small amount of electron density on carbon. So just getting a sense of when there's a difference in electronegativity, the electron density will prefer to allocate itself on the more electronegative atom. The more electronegative atom. Now, this comes up very rarely, but these are an important class of compounds in organic chemistry. If our difference in bond electronegativity is greater than 2.0, we have an ionic bond. This is no longer a sharing of electrons. This is a strict transfer of electrons to give a cation, which is positively charged, and an anion, which is negatively charged. So these are commonly, this really comes up in our organometallic compounds, organic compounds, or organic ions that are associated with a metal cation. For example, methyl lithium, or CH3Li, even though it's colloquially drawn in your textbook with a bond symbol, in reality, this methyl lithium corresponds to a CH3 anion, a negatively charged species, and a lithium cation. Let's talk a little bit about why that is. Why are we seeing a distinct cation and anion for CH3 lithium? So let's look at a carbon-lithium theoretical bond here. So carbon's electronegativity is approximately 2.4. Lithium's electronegativity is approximately 0.3. This gives us a difference in electronegativity of 2.1. So we've crossed the threshold. There's no longer even a remote sharing of electrons. And based on our electronegativity values, where is the entirety of the electron density in this bond going to lie? On carbon. That's why we, instead of drawing electron density primarily located on carbon, we draw a formal lone pair on carbon. These quote-unquote bonding electrons are not shared. They belong exclusively to this carbon. That's why we have a carbon anion. And lithium lacks these electrons, and we have a lithium cation. Yes?
So if we were to draw the structure, we draw it just like that. With
Yes.
2 lone pairs.
Yes, exactly.
Can you do it for me?
Oh, like right here?
So, but no, with the like the bond, so it would be.
So you would
Like
you'd never if you were drawing a Lewis structure, you wouldn't draw a carbon lithium bond. Instead, you draw a carbon with a lone pair and a lithium cation associated with that negatively charged carbon.
So you would never put them together in like a.
They'd be adjacent, but they would not be bonded to each other.
Okay.
So, for example, you'd write it like CH3 minus, and then the lithium plus is associated with that anion, but it's not bonded to that carbon. Does that make sense? And it really helps us think about these organometallic compounds as more ionic compounds instead of covalent compounds. So let's keep going with that. When we're looking at the difference in electronegativity between atoms, we can use this idea and describe the distribution of electron density in our bond, and that can in turn be further described using a bond dipole. So electron density is uneven between atoms in polar covalent bonds. There is a higher concentration of negative charge, a higher concentration of electron density around our more electronegative atom. So bond dipoles, which utilize delta notation, indicate that a partial charge has generated. There is a concentration of negative charge, a concentration of electron density, or a concentration of positive charge, a region lacking electron density. So a partial negative charge is assigned to the more electronegative element. And using bond dipole notation, the arrow for our bond dipole will point towards the more electronegative atom, the region with the most electron density, the partial negative charge. And it will point away from the least electronegative atom, which will be assigned a partial positive charge. So let's look at an example of a polar covalent bond and how we can represent that bond dipole using delta notation. So if we look at an HF bond, fluorine has an electronegativity value of about 4.0. Hydrogen has an electronegativity value of about 2.1. We have a difference in electronegativity of about 1.9. So this is clearly a highly polarized bond. So based on our electronegativity values, where is the, yes?
I'm just making sure the partial positive charge is still negative. Is that just a typo?
Oh yes, sorry about that. There we go. So where is the majority of our electron density in this bond going to lie? Which atom is going to have more electron density associated? Fluorine, exactly. So if we were to look at how the electron density is distributed in a hydrogen-fluorine bond, the majority of the electron density is going to lie on fluorine. And a very small amount of electron density is going to lie on hydrogen. Now, if we have a large amount of electron density distributed on fluorine, are electrons positive or negative?
Negative.
Negative. So what partial charge are we going to start to develop? Partial negative, exactly. It's indicating we have an excess of electron density on that atom. Likewise, since hydrogen has less electron density than usual surrounding it, what kind of charge will it generate? It has less electrons than usual. What? Partial positive. It's electron deficient. Using bond dipole notation, we draw an arrow going from the partial positive region to the partial negative region. The arrow points towards the atom or towards the portion of the molecule with the most electron density. Now, we can observe bond dipoles based on the fact that these molecules that are polar, that have a net molecular dipole, will align themselves in an electric field. So there's a clear unbalanced distribution of charge in our molecule, and as a result, this polar molecule will respond to an electric field. Let's look at a few other types of bonds and identify the bond polarity. It's really important to get a sense of where the electron density is going to lie in different types of bonds. So for example, I'll start us off with a carbon-oxygen bond. So thinking about our trends in electronegativity and taking a look at the periodic table, let's flip to the periodic table. So which element is farther to the right on the periodic table, carbon or oxygen? Oxygen. So based on that information, we would expect oxygen to be more electronegative and our carbon-oxygen bond to be polarized towards our oxygen atom. So we'd put a delta minus on oxygen and a delta plus on carbon, indicating carbon would be the atom with less electron density and oxygen being the atom with more electron density. I'd like us to go through this carbon-phosphorus bond example next. So looking at a carbon-phosphorus bond and consulting your electronegativity table, would someone like to tell me which of these two atoms is more electronegative?
Carbon.
Carbon, exactly right. So the carbon's electronegativity value is approximately 2.1 and phosphorus is about 1.8. So carbon is more electronegative than phosphorus. So if we think about a carbon-phosphorus bond, what direction is it polarized? What region has the most electron density in this chemical bond? Carbon or phosphorus? Carbon, exactly. And this is really unique, and it stems to the unique properties of these molecules containing carbon-phosphorus bonds. What I'd like you to do in about 1 to 2 minutes is to take a look at the next 3 set of bonds and draw and indicate the more electronegative atom and indicate using bond dipole notation the overall bond dipole. Any questions? Yep, that's good. Any questions? Looks good. Any questions? Yep, looks good. So I saw a lot of reasonable answers so far. Everyone's pretty fast with this. So let's look at a carbon-nitrogen bond. Which of these two atoms is more electronegative? Which element is farther to the right on the periodic table? Nitrogen. So which direction is our bond dipole going to point? Towards nitrogen, exactly. This would have a delta minus, this would have a delta plus. So nitrogen's more electronegative. So the majority of the electron density found in this chemical bond would prefer to lie on nitrogen. Sulfur-oxygen bonds are an interesting one. In general, does electronegativity increase or decrease as we move down the periodic table? As we move, it decreases, right? So which of these two elements, sulfur or oxygen, is more electronegative?
Oxygen.
Oxygen, yep. So our bond dipole will point towards oxygen. Lastly, carbon-magnesium bond, or bond in quotes, shows up in a lot of Grignard reagents. It wouldn't quite be correct to draw this as a formal covalent bond, but nonetheless, which of these two elements is more electronegative? Carbon. Yeah. So we draw our theoretical dipole towards carbon. In reality, what would a more accurate depiction of this bond be? Is there really a sharing of electrons? No. So we'd really draw this as a carbon anion associated with a magnesium cation. So this is commonly found in reagents known as Grignard reagents. Any questions on electronegativity and bond polarity? Does everyone understand why this last example is not a formal covalent bond? Because the difference in electronegativity is large, and it's between a metal, magnesium, and a non-metal, carbon, organometallic. Yes?
Will we need to know this for more than two atoms, or is it always in pairs?
It's always in pairs for bond polarity. And what we're going to do later on is use bond polarity together with molecular shape to identify molecular polarity. Okay. So with this idea of bond polarity established, what we're next going to do is we're going to really do a deep dive into the nature of chemical bonding. And we're going to talk a little bit about valence bond theory and molecular orbital theory. And the real goal of this section is to get a sense of describing electron density, describing the location of electron density in chemical bonds, and getting a sense of how chemical bonding is related to molecular shape and the distribution of electron density. That's our goal. So let's start first and foremost with this basic idea. So a chemical bond consists of an electron pair shared between two atoms, right? That's a fundamental nature of a bond. It's a shared set of electrons. So for example, if we have a hydrogen-hydrogen bond, that line between the two hydrogen atoms represents how many shared electrons? 2, okay? So to have a bond, we need to share 2 electrons between our atoms. Now, in the valence bond MO theory perspective, we're going to establish a new rule. So in general, a chemical bond is formed by the overlap of 2 half-filled atomic orbitals or hybrid orbitals. Okay, so let's unpack that a little bit. So first and foremost, for this hydrogen atom, right? A hydrogen atom has how many electrons to its name? 1, right? So then, what is the first orbital that we fill for hydrogen? Yep, the 1s. So we have our 1s orbital, and it has 1 electron. So we've drawn that here in pictorial form. The 1s is spherical. It has 1 electron. Is it half-filled? Yes. So if we overlap it with another 1s orbital that is also half-filled, we will generate a chemical bond and what we call a bonding orbital. We'll unpack that in a moment. So just as a general rule, to form a chemical bond from the perspective of valence bond and MO theory, we are going to overlap 2 half-filled orbitals. Okay. So let's talk about the different types of bonds. So they fall into 2 major classifications. We have our sigma bonds, and the key feature of a sigma bond, it's an overlap of orbitals directly between the bonded atoms. This is along the bond axis. So in this case, I'm showing you the overlap of p orbitals. So if we think about this bond that we're forming between these 2 oxygen atoms, so if we want to form an oxygen-oxygen single bond, is our overlap of orbitals directly along this bond axis? Is it directly between our oxygen atoms? Yeah. So we call this a sigma bond. I'd like you to colloquially view sigma bonds as quote-unquote single bonds. It's a nice little mnemonic that I use to help me remember and identify sigma bonds. Single bonds, by definition, are sigma bonds. Now, your double and triple bonds are made up of pi bonds. And a pi bond is very specific. It's the overlap of unhybridized p orbitals perpendicular to the bond axis. Now, there's one other little nuance I want to add. This can also include d orbitals, but we do not see a ton of that in this class. That's primarily in inorganic chemistry. Now, in this case, we have our oxygen, just one moment. We have our oxygen-oxygen single bond. So this single bond is our sigma bond. Let me make that a little more clear. And now our double bond is our pi bond. So this double or triple bond consists of a pi bond. Each additional bond is an additional pi bond. Now, as we notice from this picture of a pi bond, is it directly along the bond axis? Is it directly between our oxygen atoms, or is it parallel to the bond axis? Parallel. It's above the bond axis. Okay, perfect. And I like to think of our pi bonds as our double or triple bonds. Just a mnemonic to keep in mind. Any questions so far? Okay. So with this idea that to form a bond, we need to overlap two half-filled orbitals, we're now going to get to a very critical point that I want you to remember and know how to draw. So the overlap of atomic orbitals or hybrid orbitals. So for each orbital that we put in, if we put two orbitals in, we get two unique orbitals out. We get what's known as a bonding molecular orbital and an anti-bonding molecular orbital. Now, there are two key features of this process. Number one, energy is conserved. So, your bonding orbital is lower in energy, and your anti-bonding orbital is higher in energy. The amount and the energy that an anti-bonding orbital is increased is the same as the energy that our bonding orbital has decreased. So we haven't gained an inherent benefit from this orbital overlap, just in terms of our two orbital energies. However, we do gain a benefit if our electrons end up in lower energy bonding orbitals. So that's our goal. That's the reason why we form bonds, to put electrons in lower energy states. Does that make sense? Okay, so we get two different types of orbitals. Bonding, which is lower in energy, and anti-bonding, which is higher in energy. Now, the main draw of this process is that electrons are placed first in the lower energy bonding molecular orbital. We fill our orbitals from lowest to highest energy, just like we did when we were writing electron configurations, right? We filled from lowest to highest. Now, if we look, for example, at a hydrogen-hydrogen bond, our first hydrogen atom consists of a single electron in a 1s orbital. So let's draw a picture of that. So we have two electrons, each in a separate 1s orbital. When we overlap these orbitals, we generate a bonding molecular orbital. And just like all the other orbitals that we have discussed in this class, this bonding molecular orbital can hold two electrons. Each orbital can hold two unique electrons. Now, considering that our bonding orbital is lower in energy, have our electrons overall ended up in a lower energy state? Yes. Bonding electrons are lower in energy than non-bonding electrons. So, with that in mind, we're going to start to look at more complicated examples of orbital overlap. So, let's do a deep dive now into our s orbitals. How can our s orbitals overlap productively? So, s orbitals can only overlap in one major way. They can overlap to give sigma bonds. So the s orbitals can overlap, and you get a bonding orbital and an anti-bonding orbital. S orbitals can only form sigma bonds. This is your stereotypical example looking at the hydrogen-hydrogen single bond. Now, p orbitals are far more interesting to discuss. So for our p orbitals, let's take a moment and let's think. How many p orbitals do we typically have to work with? How many p orbitals do we have in each major shell? 3, exactly. So we have 3 major p orbitals to work with. So we have a total of 3 p orbitals to work with. And these can all be used for bonding. Of course, we can use one of our p orbitals to overlap to form a sigma bond. We can overlap along the bond axis. This would, for example, be describing our oxygen-oxygen single bond. Sigma bonds, single bonds. Okay. However, after using up our first p orbital, do we have 2 other p orbitals left over that we can use for bonding? Yes, we do. So then, we can overlap these leftover p orbitals and engage in what are known as pi bonds. So p orbitals can also overlap to give pi bonds. Since we have 2 p orbitals left over to work with, how many pi bonds can we make? How many overlaps can we make? 2, yeah, because we have 1, 2 p orbitals to work with and overlap with other p orbitals in other atoms. So then we can form 1 single bond, and how many double or triple bonds can we form? What's the maximum number of bonds we can form then? So 2 pi bonds plus 1 sigma is 3. So we can form up to 2 pi bonds and 1 sigma bond. Does that make sense to everyone? This helps explain a little bit why you often don't see a quadruple bond. And we'll talk a little bit about when you can see quadruple bonds, as they're quite rare. So just to reiterate, 2 atoms can form a maximum of 1 sigma bond and up to 2 pi bonds. So to check that we're all on the same page here, let's look at N2, which involves a nitrogen-nitrogen triple bond. So this is N2. So then, I'd like you all to tell me how many sigma bonds are found in this molecule. How many? 1 sigma bond. And then how many double or triple bonds do we see? How many pi bonds? 2 pi bonds. So we have 1 sigma and 2 pi bonds. Perfect. Does that make sense to everyone? Okay. Now, we're going to take this a little bit further, and we're going to start to think a little bit about how do atoms maximize bonding? How do we maximize the number of half-filled orbitals that we have to overlap? Because ideally, we want to form bonds. We want our electrons in lower energy states. So, just to reiterate, to form a bond, 2 orbitals must be half-filled, they must have the proper geometry, and they must be close in energy. Okay, so let's look at CH4. So let's look at carbon, and let's take a real deep dive here. So what orbitals are filled with electrons in carbon? So if we go from lowest to highest energy, starting from our 1s, 2s, and 2p. So do we have electrons for carbon in our 1s orbital? Yes. We have 2. We have 2 electrons in our 2s and 2 electrons in our 2p orbitals. Okay, so from this picture, let's now look at the shape of these orbitals. The 1s, is it going to be big or small? Small, very small. So we're going to draw this in blue. as just very, very tiny orbital with 2 electrons. Is our 2s going to be larger or smaller? Larger, yep. So here's our 2s, and our 2s has 2 electrons in it. Okay, how many 2p orbitals do we have to work with? How many 2p orbitals do we have to work with? How many total do we have? 3, and how many of them have electrons? 2. Okay, so let's draw them out. Again, they have different shapes, different geometries. And it's important because in order for orbitals to overlap, do they have to be in the same region? Do they have to actually be able to touch each other? Do you have to be able to overlap in order for there to be an overlap? Yes, so geometry is really important. Okay. So let's fill in our electrons, and now we're ready to discuss. Okay, so we have our picture of carbon. So how many half-filled orbitals do we have? How many orbitals do we have that are capable of bonding? 2. We have 2 half-filled orbitals. Does everyone see them here? So following just our valence bond model, how many bonds can carbon theoretically form? 2. Now, obviously, we know carbon can form more than just 2 bonds. And the way that carbon goes about forming multiple bonds is by taking its atomic orbitals and generating orbitals that have the correct shape, energy, and number of electrons for efficient bonding. And we call this hybridization. Now, what is hybridization? We're going to take these atomic orbitals and we're going to mix them, combine them together to get orbitals with an average shape and energy known as molecular orbitals. Let me rephrase, known as hybrid orbitals. So atomic orbitals are combined, hybridized, to give hybrid orbitals with the proper geometry and energy for bonding. So let's show this for carbon. Let's draw a picture. Now, key features of this idea. The molecular geometry, the shape of our molecules, depends on the shape of this orbital overlap and the geometry of our orbitals that we use for bonding. Now, just like when we discussed bonding and anti-bonding orbitals, there are a few rules that we have to discuss. First and foremost, the number of atomic orbitals that we put in equals the number of hybrid orbitals that we get out. However many orbitals you put in, you get the same number out. Finally, the hybrid orbital has the average energy, position, and orientation of the combined atomic orbitals. And this is where we can really start to show this. So let's suppose we're looking at carbon here. Let's suppose we're looking at carbon. So we have our 2s orbital, and we have our 2p orbitals. Now, if we combine them together and hybridize them to make what's known as Sp3 hybridized orbitals, what we're doing is we're taking this s orbital and combining its energy and geometry, its shape, with these 3 p orbitals. That's why it's Sp3. So how many total orbitals have we put in? How many total orbitals are we mixing? We mix this s and these 3 p orbitals. 4. So how many hybrid orbitals will we get out? 4, exactly. Now, if I said that they have the average energy of our atomic orbitals, where should I draw my hybrid orbitals? Should they be higher or lower than our 2s?
Oh,
Higher, okay. And should they be higher or lower in energy than our 2p's? Lower. Okay, perfect. So they're slightly lower than our 2p's and substantially higher than our 2s. And the reason for that is how many more, do we have more p orbitals or more s orbitals? P orbitals. More p character, higher in energy. Additionally, what's another feature of p orbitals? Are they long or are they short and stubby like an s? They're long. So would we expect these hybrid orbitals to be long or short and stubby? Long, yep. So they're longer, substantially longer than an s and shorter than a p orbital. So we draw each of these hybrid orbitals, and you can prove this using geometry, but I'd just like you to get this idea that each of these hybrid orbitals that we generate has an average shape from all of these combined orbitals. And we call these hybrid orbitals Sp3 orbitals. Now you may say, what's the point of all this? Because as we discussed, when we mix these orbitals together, we haven't actually gained any energetic benefit. However, thinking about carbon with its 4 electrons in these valence orbitals, 1, 2, 3, 4, we still have 4 electrons in these orbitals, right? So now that we have these new hybrid orbitals, where are we going to put our 4 electrons? Yep, and these hybrid orbitals all have the same energy. So if we want to fill these orbitals, do we fill empty orbitals first or full orbitals? Empty. So taking our 4 electrons, 1, 2, 3, 4, how many half-filled orbitals do we now have?
I mean,
All of them. We have 4. So how many bonds can this Sp3 hybridized carbon atom now form? 4. Exactly. Hybridization is a means of generating orbitals that are capable of forming bonds. And as we discussed, bonding is favorable. The electrons in bonds are lower in energy. Now, one thing that I'd just like you to appreciate is that hybridization and MO theory coupled with valence bond theory help explain many of the observed bond angles and molecular geometry. Do you notice how these hybrid orbitals have a 3D shape? They are pointing in certain directions. They're arranged in certain regions of space, right? And that in turn affects what direction the bonds are arranged in space, right? Because how do we form a bond? What are we doing? We're taking orbitals and we're overlapping them. So they overlap in the 3D region of space where the orbitals are present. Okay. So this is really powerful stuff when you think about it. What I want you to know how to do is to draw these hybrid orbitals, and we'll have some fancier pictures in a moment, and know how to draw these atomic orbitals. Since our goal is to say, in our organic molecules, where are electrons located? How is the electron density distributed? Yes?
So just to clarify, we started out with the 4 electrons on the left and 2
Yeah.
s and 2
Yeah.
and then we hybridized combine them,
Yeah.
we spread them out over the 4 now available.
Yes, exactly. Because we still have 4 electrons and we follow the same orbital filling rules. We fill from lowest to highest energy. Yes?
So this is for the carbon and it's not bonded to anything yet?
Not bonded to anything yet. This is the hybridization process, and after that we're going to show the orbitals overlapping to form bonds. Yes?
I'm sorry, you said know how to draw the hybrid orbitals and what else?
Know how to draw the hybrid orbitals and the atomic orbitals. And we'll show orbital overlap in detail in a moment. Okay, so let's break out some fancier pictures and let's discuss our first major subclass of hybridization that we call the Sp3 hybridization. So in the Sp3 hybridization, as we've discussed and previewed earlier, we take 1 s orbital and 3 p orbitals. And in turn, if we put 4 orbitals into this process, how many do we get out? 4 in, 4 out. And as you notice here, pay special attention to their 3D shape. Does everyone notice how each of these sp3 orbitals has a distinct directionality and a distinct shape? Okay, perfect. So the sp3 hybridization, and when you think sp3, the sp3 hybridization correlates directly with the molecular geometry or electron pair geometry of tetrahedral. Let me write this below. So there's a direct correlation, a direct relationship between the hybridization and the overall molecular shape, how bonds are arranged. And to help you see this, does everyone notice when we put these four sp3 orbitals together in 3D space, we get a tetrahedral shape. So there's a relationship between hybridization and molecular geometry, molecular shape. So let's discuss a few more aspects of the sp3 hybridization that I'd want you to remember and appreciate. So, from an orbital mixing perspective, we are combining one s and 3 p orbitals to get out 4 hybrid orbitals. A key feature of these hybrid orbitals, do they have the same or different energy? Same. They're degenerate in terms of energy. Okay, perfect. Now, let's discuss the sp3 hybridization in a little more detail in terms of the shape of these individual orbitals. So when we look at these p orbitals, just one moment. These are long and they're higher in energy. So the more p orbitals that you combine in hybridization, the higher in energy and the longer your hybrid orbital will be. So just remember p character, long, high energy. Why? Are p orbitals in general longer than s orbitals? And are they higher in energy? Yeah. So this will really come to head when we start to look at other hybridizations. So let's take a look at a few other hybridizations. Now, just like our model, where we took atomic orbitals and overlapped them with other atomic orbitals, we can form bonds by combining an atomic orbital, such as a hydrogen 1s orbital, which we'll draw like so. Let's fill in our 1 electron. And instead of overlapping it with another hydrogen 1s orbital, we're going to overlap it with an sp3 hybrid orbital. Does that change anything about our overall process? Are we still forming a bonding and anti-bonding orbital? Are we still making a bonding and anti-bonding molecular orbital when we overlap them? Yes. The only thing that's changed now is this is a bonding orbital between an sp3 orbital on carbon and a hydrogen 1s orbital. The process of orbital overlap to form a bond is still the same. Let's draw a picture of an sp3 orbital. Let's draw a picture of the sp3 orbital. So it's going to be a long orbital with directionality, and that orbital has 1 electron to its name. Now, to showcase this orbital overlap, let's draw out a picture of this orbital overlap down below. So suppose we have our carbon atom. This carbon atom has its sp3 orbital, and this sp3 orbital is going to overlap with the hydrogen 1s orbital. That in turn forms a sigma bonding orbital. So this interaction overall, we'd label as a sigma carbon sp3 plus hydrogen 1s. And how many electrons are in this bonding orbital? We took one electron each, so how many electrons are in this bonding orbital? 2, exactly. Exactly right. Does that make sense to everyone, how this process of orbital overlap works? Now,
So they wouldn't be overlapped. So the electrons won't be in the pocket where they're both.
they're
on the other side.
so I'm going to talk about that in a moment. So this is the process when we're overlapping the orbitals. To draw out the formal sigma bonding MO, the formal sigma bonding MO, we'd instead draw a single region of electron density between carbon and hydrogen containing 2 electrons. And this would be our sigma carbon sp3 plus hydrogen 1s. And the overall molecular orbital has energy based on the combined hybrid and atomic orbitals. Okay? Yes.
So, just to make sure.
Yeah.
The way you have it, first way you drew it.
Yes, is just showing here are the 2 orbitals we're overlapping.
Okay.
They're in the right 3D space to overlap. And when they overlap, we're going to form a sigma bonding MO. What else do we make? And this is not often brought up in 101. What other orbital are we making? Looking at this picture. Bonding and antibonding. And the antibonding orbital, I'm going to draw in a different color, doesn't have any electrons right now, but it's still present and accessible for chemical reactions. And it can be affected in different reactions. It's really critical to know that this antibonding orbital is on the exact opposite side of our bond. So if we were to draw our antibonding orbital, it would look something like this, and we call this the sigma star carbon sp3 plus hydrogen 1s. If there's anything that you take away from this picture, it's this idea that the antibonding, the sigma antibonding orbital is behind the bond, behind your sigma bond, on the exact opposite side. We don't often draw these in our orbital pictures because then the pictures would get really cluttered quite quickly. I just want you always to remember the sigma bond, the sigma star, the antibonding molecular orbital is behind your bond axis on the exact opposite side. Everyone good so far? Yes.
Would there be another one behind the hydrogen? Or is it just the carbon?
There would also be one behind the hydrogen, but in this case, this antibonding orbital is centered behind the carbon because the carbon is contributing the hybrid orbital. And but yes, technically there's also a little bit of electron density sitting. There's also an empty antibonding orbital sitting behind the hydrogen. It's much less accessible because it's much lower energy compared to the carbon. Yes, yes. So this whole thing would be our antibonding orbital, but the attacks typically occur centered around carbon.
If you were to give us an example on this,
You'd worry more about the carbon.
the carbon.
Yes. Yeah. We don't typically draw the antibonding orbital centered on hydrogen because that's often not where that's often at a location where attacks don't occur in many reactions. But it technically is present. So let's take a look at a few other cases of hybridization, and let's start to relate hybridization to molecular geometry. So when we look at the Sp3 hybridization, the Sp3 hybridization involves an atom with 4 electron groups around it. The way that I like to think of an electron group is either a single bond or a lone pair. We're not concerned with double or triple bonds in the electron group counting method. Because as we discussed, double and triple bonds, are they sigma or pi? A double or triple bond, is that a pi? Yeah, and we don't need to hybridize to form pi bonds. Now, Sp3 hybridization corresponds to a tetrahedral electron pair geometry with a 109.5 degree bond angle. As to reiterate again, Sp3 orbitals are long and relatively high energy orbitals. Now, to take a look at a few orbital overlap pictures, there are 2 main ways of describing orbital overlap. You can either draw the molecular orbitals or the individual atomic and hybrid orbitals. Both methods are fine. The main goal of this process is just to see how is our electron density distributed and what is the directionality of how our electrons are shared. Where are our bonds located in our molecule, and how are our bonds arranged in 3D space? Now, if we compare the structure and the orbital pictures for CH4 methane versus ammonia, which is NH3, what do we notice that's quite special about ammonia? What is one of our hybrid orbitals being used for? What is it holding? Lone pair, exactly. So we have a lone pair in one of our hybrid orbitals. And if we're really clever, we can utilize this idea of hybridization, valence bond theory, and MO theory to help explain why there's a lone pair sitting in that hybrid orbital. So that's what we're going to do next as a representative example. And this is going to help explain why nitrogen likes to form 3 bonds and has 1 lone pair to do. So let's do just that. So as our first example, let's take a look at methane and let's try to fully describe the bonding in methane. So we've already hybridized our carbon atom and we formed 4 hybrid orbitals. So what I'm first going to do is I'm going to draw out my hybrid orbitals. So I'm going to draw out my carbon atom, and here's my first hybrid orbital, which is Sp3 hybridized, and I need to draw out 3 more. 1, 2, 3. Okay? So far, so good. Each of these hybrid orbitals has 1 electron to its name. 1, 2, 3, 4. Now, from our hydrogen atoms, each of our hydrogen atoms, so each of our hydrogen atoms has electrons in what orbital? What orbital? S, more specifically, the 1s. So let's draw out our 1s. So this is our hydrogen 1s orbital. And this 1s orbital has 1 electron to its name. Now, we can overlap this sp3 orbital from carbon and the hydrogen 1s orbital to form a bond. And we describe this bond, since it's this orbital overlap, or this bond, since it's along the bond axis. Is it a sigma or a pi bond? Sigma, exactly. So we'd call this, since this is an sp3, sorry about that. There we go. We'd call this overall orbital overlap a sigma carbon sp3 plus hydrogen 1s orbital. Now, you can draw this orbital overlap as either overlap of two atomic or hybrid orbitals, or you can draw the MO. Both are fine. Now, we can repeat this process for our other 4 hydrogens. You change the color so it's more appropriate. And in turn, we have a complete description of the orbital overlap and bonding for methane. Any questions so far? So again, we hybridize to make half-filled orbitals. We overlap them with half-filled atomic or hybrid orbitals. And this orbital overlap is what a bond is made of. This is a chemical bond. Okay, so with that orbital picture out of the way, we can in turn explain the geometry of methane by virtue of how these sp3 orbitals are arranged in 3D space. So the hybridization and geometry are inextricably linked. Now, some of you were asking, and let's try to answer the question, why does nitrogen have a lone pair? Why is there a lone pair in one of these hybrid orbitals for nitrogen? So let's do this exact same process for nitrogen. Let's take a look at how many electrons nitrogen has to work with and what happens when it hybridizes. So comparing carbon and nitrogen, how many electrons does nitrogen have to its name? 5. Nitrogen has 5 valence electrons to its name. So just to help everyone see that, so nitrogen has an atomic number of 7. It's 1s2, 2s2, 2p3. It's a 5a element, so it has 5 valence electrons. So just like in our carbon example, the inner shell electrons, or our core electrons, they're close to the nucleus. They aren't accessible for bonding. The only orbitals and the only electrons that are sufficiently high in energy and far enough away from the nucleus to engage in bonding are our valence electrons and our electrons in valence orbitals. So then, looking at these 5 electrons, if we hybridize nitrogen to make, and we hybridize nitrogen to adopt the Sp3 hybridization, we take these 5 electrons and place them into our 4 hybrid orbitals. But what has changed here? Because we have 5 electrons, what ends up in one of our hybrid orbitals? Yes, we have a completely filled orbital. And this completely filled orbital is a lone pair. And more specifically, it's a non-bonding lone pair. Does that make sense, Tara? The relationship between the valence electrons and the number of lone pairs when it hybridizes? So then, my question to all of you is, how many bonds can this nitrogen make? 3, exactly. It can make a total of 3 bonds. More specifically, it can make 3 single bonds, 3 sigma bonds. Okay, so things are coming together now. So, just another side note, if we compare this lone pair in the 2s orbital to the lone pair in this hybrid orbital, do these electrons, comparing atomic versus hybrid orbital, do these lone pair electrons have the same or different energies? Different, right? We visibly see on the energy chart that they have different energies, right? And this brings up another point that's going to be critical in our discussion of acid-base chemistry, and it's this idea that the energy of an electron lone pair depends on the orbital that the lone pair is located. So just always keep in mind, lone pairs are not created equal. Depends on what atom they're located, what the hybridization of that atom is, and how that atom is participating in bonding. Okay. One last note that I want us just to keep in mind here. If we think about these s and p orbitals and these hybrid orbitals for nitrogen, are these the exact same energy as the orbitals found in carbon? Would these be the same or different? So when we just different, right? And that's because different atoms have different nuclear charge, and as a result, they have different orbital energies. So the relative energies are the same, but for different atoms, the exact orbital energy is a little bit different. Does that make sense to everyone? Okay. We'll draw on a lot of these nuances in a moment. So, what we're next going to take a look at, and what I want us to discuss briefly, is to try to get a sense of what would happen if we take oxygen and fluorine and hybridize them to adopt the Sp3 hybridization. And what I want you to tell me for these two distinct elements, these two distinct atoms, how many bonds do we prefer to form, and how many lone pairs would we predict each of these atoms to have? And I would recommend starting with your atomic orbitals. Really, the beauty of this theory is it helps explain the bonding trends that we've seen throughout this class. Any questions? Yeah. Yeah. And that matches what we see in our day-to-day lives. Any questions? So how many valences does oxygen have? Yep, exactly. So if you have 4 orbitals place 6 electrons, that's going to help. Oh, yep. If that's good. And for hybridization, we're only going to use the outermost 2s and 2p. Yep. That's good so far. Any questions? Yep, that's good. So I've seen a lot of reasonable responses so far. So let's talk a little bit about this. So how many valence electrons, outermost electrons, does oxygen have to its name? 6. Yep. So our atomic orbital picture looks something like this. 2, 4, 6. When we hybridize oxygen, we're going to generate a total of 4 hybrid orbitals. So these are our Sp3 hybrid orbitals. And into these hybrid orbitals, we're going to place how many electrons? 6. So, following that logic, let's fill our hybrid orbitals. 1, oh, that's the wrong color, but let me rewrite this. Okay, there we go. 1, 2, 3, 4, 5, 6. So how many lone pairs would we predict for this Sp3 hybridized oxygen? 2. So we'd have 2 lone pairs. And how many single bonds, how many sigma bonds can we form? 2. As I discussed, how many bonds does oxygen typically like to form? 2. And how many lone pairs does oxygen typically like to have? 2. Does this match the observed data in our physical world? Perfect. So for fluorine, fluorine has how many electrons to its name? 7. Yep. 2, 4, 6, 7. We are then going to hybridize fluorine. Fluorine doesn't typically adopt an Sp3 hybridization, but I'm just showing you for completeness. 1, 2, 3, 4 hybrid Sp3 orbitals, and we're going to fill those orbitals with our 7 electrons. Filling these orbitals, 2, 4, 6, 7. How many lone pairs would we predict fluorine to have? 3. And how many sigma bonds? How many half-filled orbitals? 1. So we have 3 lone pairs, and then 1 bond, which also matches our predictions, right? Halogens and fluorine likes to form 1 bond and have 3 lone pairs. Okay, so you can explain the bonding trends and bonding motifs that we've discussed earlier in the Lewis structure section of our course, utilizing valence bond and molecular orbital theory. Yes?
How would we notice the Sp3 hybridization?
So it depends on the exact bonding required for your molecule. So the reason why, so it's best to think of hybridization not as the atom will hybridize to adopt a bonding arrangement and an arrangement of atoms that matches the observed molecular geometry. So it's best not to think of it as causal, but hybridization is our way of explaining here's the geometry and here's the bonding that we observe for this molecule, and thus this is the hybridization of our central atom. Does that make sense? So it's not like we're picking a hybridization at random. The hybridization is based on the molecular shape and the bonding arrangement, right? Does that make sense? Okay. And we'll see this when we discuss the Sp2 hybridization. So what we're going to do now is, so we've already explained the orbital picture for ammonia. So we're going to continue on. Just as a refresher, from our observations for nitrogen, when nitrogen adopts the Sp3 hybridization, one of the hybrid orbitals contains a lone pair. That's the takeaway to keep in mind. So let's now discuss the next major hybridization, which is the Sp2 hybridization. As its name implies, how many s orbitals are we mixing together? Just 1. So we're taking 1 s orbital. And how many total p orbitals are we combining? 2. Okay. Since we put 3 orbitals into this hybridization process, how many orbitals do we get out? 3. Now, I'm going to draw something that we are missing here. What is missing? Is there something that's sitting, is there an orbital that's sitting around that we have not used in this process? So looking at the p orbitals, how many total p orbitals do we have to work with? 3. So there's another p orbital. And I'm just going to put it in a little box over here because it's not utilized for hybridization, but it's still present. So we have this p orbital. So at the end of this hybridization process, if we don't use this p orbital, what do we have in addition to our hybrid orbitals, in addition to our 3 hybrid orbitals? What do we have left over? Oh, what was it? Or just in general, what orbital do we have? Yep, exactly. And this is really critical. So we have a p orbital that is left over. And this p orbital can be used for bonding. Specifically, what's the hallmark type of bonding for p orbitals? What can p orbitals be used for?
Oh, pi bond.
Pi bond, exactly. So when we start to get into the Sp2 hybridization, we can start to form double bonds and start to get more complex bonding arrangements. Okay, so just in summary, we are combining, one moment, we are combining an s orbital and 2 p orbitals. 3 orbitals in, we get 3 hybrid orbitals out. And again, what orbital do we have left over? What orbital is available for bonding that we have left over? A p orbital, yes. Just always remember that. There's this leftover p orbital. And this is often critical when we discuss resonance and pi bonding and pi systems. Now, because we have less p orbitals mixed together in the sp2 hybridization, what happens to the sp2 orbital energy? Is it going to be higher or lower than an sp3?
Lower.
Lower, because it has less p character and more of this low energy s character. Additionally, drawing a picture, our s orbitals are short and stubby, our p orbitals are long and high in energy. If we have overall less p character and more s character, what's going to happen to our orbitals? If s orbitals are fat and stubby, what's going to happen to our sp3 or what's going to happen to our sp2 orbitals? Shorter and stubbier, right? So if we were to draw the overall shape of an sp2 hybrid orbital, it'll be a little bit fatter and a little bit shorter. Oops, let me draw the geometries correctly here. So these are shorter and lower energy. Okay, so it's always important to keep in mind hybrid orbitals have different energies depending on the hybridization. Does that make sense to everyone so far? And again, the directionality of these orbitals is based on geometry. Okay, let's try to utilize this idea of hybridization to help explain bonding, and let's relate the sp2 hybridization to a given molecular geometry. So when we think sp2, we have 3 electron groups. Check the time. Oh, we'll be able to cover a little bit more. The clock's 5 minutes fast. So when you think sp2, I want you to think 3 electron groups. Again, what is an electron group? What are the 2 things that qualify as an electron group? Yep, a lone pair or a sigma bond or a single bond. Okay, the sp2 hybridization corresponds to the trigonal planar electron pair geometry. And the key feature of the trigonal planar electron pair geometry is that we have 120-degree bond angles. So again, we have a relationship between molecular shape, molecular geometry, and hybridization. Again, also, sp2 orbitals are shorter and lower in energy. So then, if we start to try to form bonds with these shorter, lower energy orbitals, what will happen to our bonding electrons? Will they be higher or lower in energy? Lower, exactly. The orbital that you use for bonding affects the nature and energy of that bond. So let's take a look at an orbital picture involving formaldehyde. And let's break this down to show unique features of the sp2 hybridization. So first and foremost, we have our central carbon atom. Our carbon atom is sp2 hybridized, so let's showcase that. So starting off from carbon, we have our 2s and our 3p orbitals. we're going to hybridize them to the Sp2 hybridization. So we are going to combine an s orbital and 2 p orbitals to generate 3 hybrid orbitals. We'll draw them lower in energy than our p orbitals and our corresponding sp3 hybrid orbitals from our previous example. So these are our sp2 orbitals. We also have left over a higher energy p orbital. By definition, the p orbital is higher in energy than a hybrid orbital. Okay? Considering that carbon has 4 valence electrons, so we have 4 electrons in these valence orbitals, where do we place these 4 electrons if we wanted to maximize bonding? If we wanted to maximize 1 each, exactly. So if we just placed it from lowest to highest energy, we'd end up with the following arrangement. This is not 100% correct. To maximize bonding, electrons can be subjected to a process known as promotion, where this electron in the lower energy sp2 orbital is moved to the higher energy p orbital so that it can form a chemical bond. Just to be 100% correct. So if we're drawing out a picture of our available atomic orbitals and hybrid orbitals, we would end up with the following orbital picture. Perfect. Everyone comfortable so far? Yes.
So with promotion, is it safe to assume that electrons are more stable in bonds than lone pairs?
Yes, in general. Because a lone pair by definition is a non-bonding set of electrons. And the reason why bonds are stable is because we're getting this electron density between 2 nuclei, between 2 regions of positive charge. So it's a very stabilizing event compared to just having a lone pair where the electron density only belongs to 1 atom. Okay, so from these hybrid orbitals, which are drawn in this following orbital picture, we are capable of we have how many half-filled hybrid orbitals? How many half-filled hybrid orbitals do we have? Let's be specific. Hybrid, 3. So we have 3 hybrid orbitals. And the reason why I bring this up is these hybrid orbitals are what are we going to use to form sigma bonds and hold lone pairs. What can we do with these p orbitals? If we're using our hybrid orbitals to form our single bonds, to form our sigma bonds, the overlaps on the bond axis, what is our p orbital going to be used to form? Pi bonds, exactly. So this p orbital is in turn utilized to form a pi bond. Does that make sense to everyone? The hybrid orbitals are used for single bonds, sigma bonds, while the p orbital is used for pi bonds. Okay. With that, do you have any questions on hybridization? We'll finish up hybridization and MO theory next class session, and we'll start to both draw out orbital pictures, and then we'll discuss drawing out structures like in organic chemistry. So we're starting to go to common norms and conventions for drawing structures in organic chemistry. Because by the end of this class, you're not going to ever want to have to draw a carbon-hydrogen bond if you can help it. So we'll develop methods to quickly draw structures. Any other questions? Okay. Oh, yes.
Sorry. So when you said that the electron groups are sigma bonds and lone pairs.
Yes.
So if there's a double bond that has a sigma bond in it, right? So you count that as
Yes.
one.
Yes. A double bond is counted as 1 sigma bond and 1 pi bond.
Okay.
Exactly. Just like we see here, where this double bond, this carbon-oxygen double bond, is a sigma bond involving our sp2 hybrid orbital, and this pi bond is involving our p orbital. So double and triple bonds are the combination of a sigma bond and one or more pi bonds. Exactly. Perfect. Well, if you don't have any other questions, I'll see you again on Wednesday. Expect a quiz where you will have to draw an orbital picture similar to this and explain differences in lone pair energy and bond energy. Yes.
I'm sorry. So you want us to draw the picture that's above, not necessarily what we've
And,
been drawing
and
down there.
down here as
So
well.
you want both.
Both of these are reasonable for me to ask. Like I could ask you, for example, to describe the orbitals used for bonding in a molecule such as formaldehyde, methane, just a simple molecule where you don't have to draw too many orbital overlaps. And from drawing this picture, I'd like you to be able to label the orbitals overlapping and, for example, draw a sigma star, pi star, etc. And if you need references for the sigma star and pi star, they're found at the start of this chapter when we discussed orbital overlap. Does that make sense to everyone? What's expected of you for the quiz coming up? Also, make sure you're comfortable drawing Lewis structures as well. Since as part of these problems, it's helpful to also draw a Lewis structure as well. Beyond that, that's all I have for today, and I'll see you in lab.